Today will be our last day talking about nuclear reactions. We learned about nuclear reactions in the medical field. Then we looked at nuclear fission. The big idea with fission is breaking apart a large nucleus into two smaller pieces, usually using a neutron to start this reaction. The other idea is that when the large atom breaks apart, lots of energy is given off. This happens in nuclear power plants like the one we have down in Salem, and it also happens in the atomic bombs like we had in Hiroshima and Nagasaki. Today we'd like to talk about the second major way of changing the isotopes, and that is nuclear fusion. So again, fission was when we had big atoms and we broke them into smaller isotopes. Fusion is just the opposite. We're going to take two small isotopes and fuse them together to make a bigger isotope. Nuclear fusion. Here's the problem with nuclear fusion. Let's say we have hydrogen 2, a proton and a neutron, and we're trying to fuse it with another hydrogen 2, proton and neutron. The problem is nuclei are always positively charged, regardless of what the isotope is. So trying to bring two positively charged particles together is not going to be easy. They're going to be repelling each other with a very strong repulsive force. Now, we do know if they get close enough to each other, the nuclear strong force will kick in and bind the two together forever. But the problem is, how do we get them close enough to get that nuclear strong force to kick in? And hopefully it's obvious that if we get them moving fast enough, as they slow down, they won't slow down enough before the nuclear strong force kicks in. So the key is getting them moving very, 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 very fast. How do we get them moving fast? Well, hopefully you remember that the speed is determined by temperature. At higher temperatures, the particles will be moving around much, much faster. So the key to nuclear fusion is having incredibly high temperatures. Millions of degrees are required to have enough speed to get these particles to get close enough before they're repelled away from each other for the nuclear strong force to kick in. Once they do fuse together, they're going to release lots of energy. More energy, a lot more energy per kilogram than we get from nuclear fission. So this turns out to be the best energy source we can think of. This is one of many fusion chains that happen. The one I showed you a few moments ago is a very rare event. Hydrogen 2 is not a common isotope, so having two of them collide at a very high speed is kind of unlikely. However, this is a very common fusion chain that we might see. We take hydrogen 1 and hydrogen 1, which is super abundant, like 99% of all hydrogen is hydrogen 1. We combine it together at those high temperatures. We create energy, we create a neutrino, and we create a positron shooting out. We then get hydrogen 2, which then fuses with another hydrogen 1, because hydrogen 1 is so common. They come together and form a helium 3. This happens again over here. The helium 3s collide. Again, maybe this is not the most common, but some sort of reaction like this. They combine together, produce more energy, and produce helium 4. Now, there's a lot of different ways this can happen, but the key is that we take 4 hydrogens and turn them into an alpha particle, a helium 4. Along the way, some positrons pop out, some neutrinos pop out, some gamma rays pop out, but most importantly, we get lots and lots and lots of energy. Okay? So the net reaction would look something like this. 4 hydrogen 1s produce a helium-4 plus 2 positrons. Again, the positrons are antimatter. They eventually will meet up with normal electrons. They will vanish from the universe, and we get even more energy. The helium-4 is not a dangerous substance. So the beautiful part of nuclear fusion, when we compare it to nuclear fission, is that with nuclear fusion, our byproduct is not a dangerous thing. This is an ideal energy source. The problem with this ideal energy source is that it's extremely hard to get the temperatures needed to produce this effect. The fuel, hydrogen, super abundant. Just think about all the water on our planet, which is composed of hydrogen. So that it's easy to get the fuel. The byproducts are safe. The problem with it is achieving the temperatures needed to get this to happen. Now, there are 2 places where this does happen, and one of them is the ultimate source of all of our energy here on Earth, and that is in the sun. The sun is a giant ball of energy, gases, and it's producing tons and tons of energy all the time, and it is doing so through nuclear fusion. At one time, the sun was almost all hydrogen, and it still kind of is mostly hydrogen. And in the core of the sun, we're having so high a temperature that the hydrogen is turning into helium and producing lots and lots of energy. That energy being produced is the thing that drives our planet. It's what allows us to have weather. It allows us to have plants. It allows us to have animals. All of our energy comes from the sun. Again, even things like oil and coal and gas, they're from plants from long ago, plants and animals from long ago. So they're even energy that started out in the sun. The only type of energy that doesn't start from the sun would be when we use uranium, okay, nuclear fission. But all other energy sources emanate from the nuclear fusion inside the sun. We are trying to do nuclear fusion commercially to produce our energy. And there are lots and lots of places around the world where they are building fusion reactors. The problem is it is so hard to contain that high energy plasma that contains the hydrogen that is fusing into the helium that as of right now it's not economically viable. We need to put more energy in to create the high temperatures than we're actually getting out. But I have great faith that within the next maybe 10, 20 years, we will find ways of making fusion more practical. Being able to contain that high energy plasma using magnetic fields or lasers. The problem with trying to contain it with normal materials is the temperature is so high the materials will melt. So we need to find ways of containing it using things like magnetic fields, electric fields, or even with lasers. All right? So nuclear fusion. It is when we take small isotopes, combine them together to make larger isotopes, and then in the process create lots and lots of energy. Fission, again, is where you have a large thing and you break it down into smaller things, and once again, you get energy as a byproduct. Of the 2, fission is easier for us to do. The problem is the fuel source, uranium, is harder for us to find, and 2, the byproducts are more dangerous because they're radioactive. Fusion, easy to find the fuel, easy to deal with the products, because they are just helium, okay, alpha particles. The problem with fusion, again, is the fact that it requires such high temperatures. We have to find a way to contain it. So anyway, guys, hope you understand the difference between fission and fusion and some places where each of them were used. All right? Thank you.